Okay, so that was all really good. I would like us to just take a moment here and review how we got here, or why are we here? We're here. We want to study intelligent systems. We want to study AI. We want to study reinforcement learning. But why? We want to make, ultimately, I would say, we want to understand the mind, the great scientific puzzle of the mind, and so we have a scientific goal, a sort of humanistic goal of understanding ourselves, and we also have, a technological goal. Maybe we want to be part of what's happening in commerce today and get a job in machine learning, and AI would be part of that. But the science goal is big. It's really big, and it will be lasting. Maybe the current popularity of machine learning will pass, but the science will always remain. This will just it's a big task for us to understand the mind, to understand intelligence. And next step is, what does that mean? Well, I don't know if you remember, it's been a couple months now, what our definition of intelligence was. But basically, it's the computational part of the ability to achieve goals. And achieving goals maybe is in the mind of the beholder, and maybe it's a continuous quantity. It's not a binary one. But we want this ability to achieve goals. So then we formulated that as maximizing reward. We formulated this overall problem of an agent interacting with its world. It's a Markov decision process. So we have actions, we have states, we have rewards, we have time steps. So we have a mathematical formulation, and then we've studied it first, how you could solve it if you knew the way the world was constructed with planning methods such as dynamic programming. Then we looked at learning methods so that you could just use experience to find the right policy. And what else did we really do to structure the problem? We did value functions. Value functions have been key to all the methods, all the planning methods, all the learning methods have been to try to figure out from the state how well it's going. And then that is what you use to pick your actions. And in TD methods, you actually used it totally for learning. As you went from state to state, you noticed that some states were better than others, and you used the surprises, the little increments as you go from moment to moment to do the learning. And then we added function approximation of all kinds, tile coding, neural nets, so we could handle. We basically are at this point growing the framework. The framework was originally tabular, learning and planning, and then we grew it to bring abstraction, state abstraction, features, function approximation. And then I guess it was just last time we brought in temporal abstraction. We extended the same ideas to apply for larger ways of behaving, and I argued that this is really key to giving us things like concepts, things like perception, things like really understanding the world at various levels, multiple levels at the same time. Now, along the way, we also did n-step methods. N-step methods, n-step temporal difference methods, n-step bootstrapping. So it's not just, it's really a way it's another really a way of temporal abstraction. Temporal abstraction, remember, is abstracting over time, so we don't get trapped into thinking about single time steps, the small time step. So with n-step methods, we were saying, well, what if I do something, and then some steps arrive, and then I get a sense of how well it's done. Maybe not on the very next time step, because the next time step might be, 100th of a second. And that might be too short to figure out what's happening, to figure out whether it was a good idea to do that action. But if you wait 10 or 100 steps, n-step method, you can tell, and then bootstrap back. And today, we're going to continue with that same idea, escaping from the time step. As we did with options, as we did with n-step methods, now we're going to do it with eligibility traces. Eligibility traces are another way of escaping from the time step. And they're also, a very elegant algorithmic strategy. N-step methods they're easy to understand in a certain sense, but the algorithms are kind of ugly, and they're not like a continuous engine running moment by moment. And this we can get with eligibility traces. So I hope you will enjoy them as much as I do. So here we are in chapter 12, eligibility traces. And so first things to say about them, they're another way of interpolating between Monte Carlo and TD, so just like n-step methods. We're going to have this idea of a compound return, compound lambda return. It's a basic mechanistic idea. It's a lot like you might think of as short-term memory. What if something good happens, you say, well, what have I just done? What have I done in the last second? There must be some memory to cross that when you did it and the second later when the good thing happened. And along with this new mechanism, we'll have a new way of analyzing things in terms of the forward and the backward view. And we already talked about the forward view when we did n-step methods, but now we're going to have the backup view of eligibility traces, which is going to be a way of achieving the same result, but in a computationally cheaply and in an elegant way, a little bit less transparent. And we have to do these steps to translate from one to the other, from the forward view to the backward view generally. So you remember our summary of the first part of the book, where you had our four corners, and we explored this dimension of intermediate methods that did multi-step, and this is also where we're gonna live today. So like today we lived, in chapter 7 we did difference between 1-step, 2-step, 3-step, 4-step, all the way to infinite steps. So this dimension was the number of steps of bootstrapping. Now it's going to be the rate at which our fading trace of what we've done fades away, and the rate at which it fades away is called lambda. So here, just to remind you what we did before, we had 2-step returns. We would use a target for an error of the first couple of rewards, and then we would use the estimated value function for the remaining part of the remaining rewards. And here I'm writing out explicitly as if it was linear. So we take the inner product of the feature vector, remember, for 2 time steps later, because we're waiting 2 time steps, and our weight vector. And the n-step target means we could wait n steps and then correct. Okay, that was n-step targets. And now, if this works, our basic result was that any n-step target was a valid return. And a valid target that we could use to update towards. So now I want to say that this is true even if we take a convex combination of them. So here we take 2 valid targets, the 4-step target and the 2-step target. We take half of one, half of the other, and we have an overall target. And this is called a compound target, or compound backup. And we draw it in a picture like this. We make our backup diagram. We just have the 2 backup diagrams. There's the 2-step backup and the 4-step backup, and the mixture weights underneath. Draw a line across the top, and that's a compound backup. Okay, so we can do this with any valid target, any valid backup, we can mix it in with other backups. So here's the case that we do in eligibility traces. We're going to do, so this is what the famous algorithm called TD lambda, and we're just going to do state values. And so it's like TD0. You might have been wondering why we called it TD0. Well, because it's the special case of TD lambda, where lambda is 0. And it's a mixture of all of the n-step backups. So here's the 1-step, 2-step, 3-step, all the way. This is the infinite step one because it's where we have termination. And so we're taking all of these, we're going to mix them together, and by some weights. The weights, remember, are written across the bottom. And the weights have to sum to 1. We sum up all the weights, they have to sum to 1. And the other thing that we're designing into our weighting strategy is that we, so it goes up by lambda. There's a 1 minus lambda factor in front of all of them. But then it goes, this is lambda squared, next one will be lambda cubed. So basically, the longer the end step target, the less weight we give to it. Lambda will be less than 1. So we're going to give exponentially less to longer and longer things. The first guy has a factor of lambda to the 0, so it's just 1 minus lambda. It's got to be 1 minus lambda in order to sum to 1. Because you remember, if we just had the powers of a lambda, what would they sum up to? The powers of lambda. What? Yes, now that was a big test to see if you were really just rote learning and you said 1 over 1 minus gamma. No, of course, it's 1 over 1 minus lambda, same thing. Now with lambda, 1 over 1 minus lambda, they sum up to that instead of summing up to 1. So if we want them to sum up to 1, we've got to get rid of that 1 minus lambda in the denominator, so we've got to multiply everything by 1 minus lambda. And then they'll sum up to 1. Okay? And so this equation expresses that. This new kind of target, we're going to call it a new kind of return, actually, the lambda return, is equal to the sum of the end step targets, right? For every n from 1 to infinity, but they're going to be weighted by lambda to the n, basically. And we're going to sum all those up, and that's going to be our lambda return. Just a mixture of all the n-step targets. It's a particular mixture. It's this discounted, decaying, weighting mixture. But notice this is we're looking at the future. We're looking at say, oh, you know, my n-step target in n steps into the future, we're going to weight it up less if it's far away into the future. The first one gets the most weight. I think I have a picture of that. Yeah, here's the picture of the weights as they go out into the future. So we're sitting here at time step t. We're looking ahead as far as the end of the episode. And like the first, there's something that's fading away with as we look into the distant future. And the first thing will be worth 1 minus lambda, and the second worth will be, the second step, whatever happens then, will be worth 1 minus lambda times lambda. So here we're looking at the third one. The third one is 1 minus lambda times lambda squared. That's how much weight we give it in this lambda return. And this fades off and off and off. And eventually we reach the terminal time step. And how much weight should we give to the terminal? Well, we have to get the whole, things have to sum up to the whole discounted thing. So if all this remaining weight has to be given really to the final, the total return. Okay, and it is, so we can split it up. Here we split it up into as we look ahead into the future, how many n-step returns do we get before termination? And there's a certain number of those, and then all that stuff for after termination. That stuff after termination, that remaining part is actually this quantity. It's lambda to big T minus little t, which is sort of how long the episode lasts into the future. And you got to get the signposts right, as you have a -1. So we can break it into all these things that happen before termination and all the things after termination. And that's useful to do. If you want to think about it, here we've done the same breakup, okay? And we just want to consider some special cases. So what if lambda is 1? If lambda is 1, what's this equation, okay? Here we just substituted 1 every place there's a lambda. Okay, and so this has got a 1 minus 1 in it. So basically all that's going to disappear. Okay? This thing has 1 to some power. What's that? That's 1. So that just turns into, so the whole thing reduces to g of t. So that means the target, the lambda return target, if lambda is 1, is the normal Monte Carlo target. So it becomes Monte Carlo. If lambda is 1, we get Monte Carlo. If lambda is 0, do the same trick. Every place there's a lambda up there, we put in a 0. Okay, that's not going away anymore. This part is 0 carried to some big power that's not 0. So that's going away. You're just going to have this thing. And what can we say about, well, this has got 0 carried to power, so maybe that's going away too. So we got nothing. Except for that mathematical convention that anything carried to the 0th power is 1. Even 0 carried to the 0th power is 1. It's a really convenient mathematical convention. So do we have 0 to the 0? Is n minus 1 ever 0? Yeah, the very first one, n is 1, and so we have 0 to the 0. So we actually do get that term. The n equals 1, all the other terms disappear, but we get the n equals 1 term. And the n equals 1 term, this becomes 1, and we have g, the return from t to t plus 1. It's the, as you see over there. It's the one-step return, one-step target. In other words, it's TD0. Okay, so we have achieved, just like we did with n-step, right? N-step for n equals 1, we get TD0, and for n equals infinity, we get Monte Carlo. Well, now we get the same spectrum, but just in a little bit different way, as lambda varies between 0 and 1. And all the intermediate things give us intermediate algorithms. Question?
A four-step return is in this bias estimate for the return.
I can't quite get you.
I'm saying a four-step return is a less unbiased estimate than a three-step return. But
Yeah, generally we think the shorter the returns, the more bias you would have, right?
But we're weighting the more biased more.
Higher. We're giving higher weight to the shorter ones.
It seems to me like it should be the other way around.
Well, so it's a question, isn't it? What's the right way to weight these things? Should we weight them differently? Yeah. Yeah, why do we weight them this way? Well, if you remember our results actually was that short range bootstrapping was usually the best. You don't want to do like long range things close to Monte Carlo because they're just too noisy. Well, I guess in our earlier, we've seen both sets of results. We've seen results for the tabular case in which the bias goes away eventually. And we've seen results, some results for the function approximation case in which it still remains a question whether we want to, where we want to place the weight. Is it true with TD lambda you can only have decreasing weight? Well, actually, it's not true. So you're asking, first of all, there are several ways to do this. This is one way, and other ones have different properties. The other one, which we covered in this chapter, if you read all the way to some section after the beginning, where we covered variable lambda. With variable lambda, you can give almost an arbitrary profile. So if you, with variable lambda, you can get an almost arbitrary profile. for your bootstrapping. So it's a good question. It's not clear this is the right thing, but nevertheless, I think it's pretty close to the right thing. Just accept that as sort of a judgment rather than something that's clear, and certainly not obvious from what we've seen today. Good. Okay, so here's a sort of an algorithm. We cheat. We do it offline. We go through a whole episode, and then when everything's done, we know what all the n-step returns are at all time steps. Then we go back and we do the update. So we actually just do a simple update. The wait at time t, even though we're doing this update later after the episode is all done, we're going to do an update for time step t based on the error between the estimate and the lambda return. The key part, we had to cheat because I want to put the lambda return in here, and you can only do that once you know all the rewards all the way up to the end of the episode. But the rest, so this is the error, and that is our usual form for the gradient for a general gradient algorithm. Okay, so this is an algorithm, sort of an algorithm. I have to quote it because you couldn't do it for control, because or you delay until the end. And if some good thing or bad thing happened, you can only take into account at the end of the episode, and it would only work for episodic problems. So I'm not really happy with it, but you could do this. And we can compare this to TD lambda. And, or actually, no, we're going to compare, we haven't defined TD lambda yet. We're going to compare the offline lambda return algorithm, the first algorithm to use this lambda return, to the n-step methods from chapter 7 on the 19-state random walk. Okay? Now, 19-state random walk, you remember that? Maybe the n-step methods, and we drew these curves as a function. This is the performance measures how well you're doing basically on the first 10 episodes. And then we varied the learning rate, the step size, excuse me. And we had the one-step method, did a certain well, and if we used longer things, like a 4-step method, you would do better. But you didn't want to get too high, because then you'd be too close to Monte Carlo, and your performance would be slow on these first 10 episodes. This performance measure is emphasizing the initial performance rather than the asymptotic performance where the bias would be important. Okay, so now as we bring in we're just basically comparing, is n-step good idea, or is the lambda return a good idea, is the lambda way of mixing a good way of mixing? So we go back to this problem and just see how well you do. And what you see is that at the best values, this is a little bit better. It's just this distance is slightly smaller than this distance. But perhaps more important is just that these numbers are well, you look at like n equals 4, which is a good one, but as you get towards a high step size, it really shoots up. Whereas lambda equals 0.8, which is the best value in lambda world, as we start to get large alphas, we don't go up so dramatically and horribly. It's good over a larger range of parameters. That's what I see here. The next one over from the best one, 0.9, it also degrades gracefully, whereas n equals 8 tends to go off to poor performance. Okay, so we are running a little bit better with lambda as a way of shifting between one-step methods and Monte Carlo, TD methods and Monte Carlo. So we see that I guess is the big thing, but the pattern is very similar, which is comforting. Intermediate is best, and we're doing just a little bit better with lambda returns on this tiny problem. Who knows how other problems would go? So that's encouraging. Lambda return methods, but that's not enough, really. I don't think that should be enough for you guys. and that's why I've tried to claim that the real significance of eligibility traces is that they give you a simpler mechanism and a more elegant mechanism. Okay? And as I've talked to today, they probably haven't seen too elegant and too simple, because we have to look up into the future and calculate all these n-step returns and then add them up together. And that was conceptually clear, but it was not a good algorithm. And in this algorithm we had to wait until the end and do it offline, so that was nasty too. So we really want to go to an elegant form that achieves something like this, that gets the same advantages of the offline lambda return algorithm. Okay, so let's do that. That's what we want to do today. So I want to contrast the forward view, where we're looking ahead at all these rewards and figuring out the n-step returns. That's what we've been doing. We're riding the stream of experience as it goes off into the future, and we're looking ahead, which is going to be problematic because you can't really look ahead. You got to wait until you get there and then see where you are. But we're going ahead and sort of cheating. And then the backward view where you sit at the current time step, or maybe t plus 1, and you look back. Where have I been? And where you've been is going to be represented by the eligibility trace. So these Zs are the traces. And they're going to fade away into the past. And then you're going to shout back the TD error, and then you're going to basically take where the TD error and the trace are intersect. That's where you get learning. Okay? Let me just show a picture of that, a video of that. So this is a grid world. This is just some obstacle, never mind that. We have a start, we have a goal, and what you see in these little lines being left behind, maybe I can stop it somehow. Yeah, okay, see, it's just arrived at the goal, and it's left behind these little breadcrumbs representing where it's been. So if you imagine at the beginning of time, beginning of learning, everything is 0, and it gets a reward of +1 for arriving at the goal. +1, that's great. If it was a one-step method, it would just go back to the state preceding the goal, and an n-step method would go back n steps. Now, with an eligibility trace, we're going to go back according to these breadcrumbs. The breadcrumbs mark, well, these are action values, traces, so we're marking that in this state, you went to the right. In this state, you went up, and so on. As you get fade farther back, they get smaller and smaller, and they're updated continually, right? And they're going to fade with lambda. Actually, they're going to fade with lambda times gamma. But in a grid world, gamma is generally 1. Okay? So these, when you're in a state, you will, let's be in a state that's not the goal. You're in a state that's not the goal. You still might have a TD error at this state, because maybe you had been to the state before and you realized it was good. So when you arrive in it, you say, oh, that was good. So it's really TD error that should go passed back to all the eligible states. You leave behind little breadcrumbs, and then when TD error happens, you attribute it to those states. So actually, let me just do this slide first. So this is the algorithm. And we start with the change in the weights. Change in the weights, alpha, delta, z. Okay, so that's where we're saying, what's the trace now? And what's the TD error now? And we're saying this is a vector equation. Right, so there's going to be a trace left at each weight. Delta is our normal delta, our normal TD error. Are things working out better than I expected? This is what I expected. This is what I'm getting. Is it working out better or worse? And the trace starts out at 0, and then whatever it was in the last time step, it fades away by gamma times lambda, and then we add in the gradient. Okay? So let's look at that a little bit further. This is our eligibility trace, a new vector. Okay, it's the same size as it's the weight vector. I didn't change that to W. It's the same size as the weight vector, so it's R to the D. And Z. Now this thing, it's going to fade away. So here it is. We're looking at either one state or one parameter vector. Okay, I guess we're writing here as if we have a parameter vector, and so one of the features or one of the weights, and when we visit that weight, it's clear what it means to visit a state. To visit a feature means the feature is 1 as opposed to 0. But this equation will work with arbitrary feature values. They don't have to be 1s and 0s. But it's convenient to think about, to fix your intuitions about the case where you're either visiting or not visiting. So when you visit, your trace jumps up, and then afterwards it fades away. If you're not visiting again, it just fades away. If you visit it twice, maybe your trace jumps up even higher before it starts to fade away. And this is actually called an accumulating trace, because as you visit something more times, the trace kind of accumulates over time. There are a couple other different kinds. So that's the idea of a trace, and these equations are the accumulating trace. We're adding in the new increment, the new gradient to the existing trace, and the existing trace fades away, gamma times lambda. That's our algorithm. And this is that same algorithm in equations. And I guess I've slipped in here a little bit of theoretical result. But first I have to explain this VE bar. I've just introduced, I guess in between the two books that you've received. It's just the same thing as the mean square value error, which was defined in the first book. Mean square value error, I just got tired of writing mean square in front of everything, because there was mean square value errors, mean square return errors, there's all these mean square things, and they're just so easy to get confused. So I've just kept the informative part, the value error part, and this bar suggests, to me anyway, the idea of a mean square, an average of that thing. So then if you understand the equation starting from the right of here, well, this is the value error for a weight, and then we're going to take the minimum of that over all possible weights. So this is the best you can do. Okay, and so before, and we're going to show that how well we do with the weight vector found by TD lambda is smaller than that after it's been multiplied times this fraction. So this fraction had better be bigger than 1, because, well, there's no weight that does better than this weight vector. And do you remember, do you remember earlier on we showed a result that was very much like this, and it was for TD 0. So it should be this very same result when lambda equals 0. So when lambda equals 0, this term goes away, and just 1 over 1 minus gamma. So that was our previous bound. Now we can get a slightly better bound, depending on lambda. What's the best value of lambda, according to the bound? You don't want it to be 0. You want it to be as big as 1, because then you'd be Monte Carlo. And as we have often discussed, if you're talking about asymptotic performance, you're going to do best with Monte Carlo. It's a terrible choice. Terrible choice, but it's going to be best asymptotically. Yeah, same thing here. Now we can just talk about it more generally. This is a strict generalization of that result. Now, when we go to function approximation, these are semi-gradient methods. Here we're just drawing it out as an algorithm. So I want you to, it's appropriate to look at it here. We can appreciate the sort of elegance, the sort of continuously running version. Let's just go through this a little bit at a time. So we're just trying to learn the value function for a given policy so far. So we're trying to learn v hat that approximates v pi. So we have to receive pi. And we also have to receive the form of our function approximator. V hat could be a neural network. It could be tau coding. It could be any other linear function approximator or nonlinear function approximator. So we have to receive that approximator. And formally, that approximator is something that takes a state and a parameter in r to the d and reduces it to a number. So it's a function, and we're gonna try to find this parameter. We'll define. So it's over S plus, meaning we're allowing the terminal state to be input to the value function, but we're also going to require that if we do ever give it the terminal state, it's got to give us 0. Okay, so terminal states have value 0. We initialize the weights arbitrarily. It doesn't matter for the theory, which you might initialize them to 0, or maybe optimistically or pessimistically for safety. And then for each time step that goes for each episode, you have to start in the standard state for the episode, and our eligibility traces have to start at 0 at the beginning of each episode. And then you get into the mechanistic part where we're just going to do these steps over and over again on every time step. And if there is only one, if there are no episodes, then there's only one episode. So we're just going to spend all of our time doing these steps over and over and over again. And those steps are: pick your action using your policy, take it, see what happens, and now update your eligibility trace vector. It's a vector equation. The vector bold z is take the whole bold vector before and decrease it by gamma times lambda, which are both less than 1 or equal 1. And then we add in the gradient for that state that we took our action in. We compute the TD error, reward gamma times the new guess minus the old guess. We do the weight update equation, alpha delta z, and then we just, now what used to be the new state is considered the old state, and we repeat, unless that state was terminal, in which case we'd be done. Okay, so that's the whole algorithm. Just runs like that continuously. There's no messy indices. Everything is present, and you're just using the things that are present right now. And you do these you have to update 2 vectors. Not only W, we also have to update Z. So it's maybe twice as much work. Adam.
Why do we have to set Z to 0 at the beginning of the episode?
Well, what does that mean, that we set Z to 0 at the episode boundaries? Okay, it means that if you see some states, because we don't have any actions really yet, if you see some states and then you have the end of the episode, you get blamed for what happened during the episode. But if your traces continued past the episode, you'd really be assigning credit to the states on the previous episode. Yeah, and you don't want to do that, generally speaking, because they're not responsible for what happens. You have a question?
Yeah, so how is TD lambda equivalent to offline TD we saw earlier?
How is it equivalent to the offline lambda return? It's because it's not, right? It's not quite the same, because it doesn't, it's not cheating. It's only using the information available now. And so you might ask, how much of a penalty did you have to pay to not cheat? And so basically the story for the rest of the lecture is you do lose something, but through algorithmic tricks, we can get some of it back, and then eventually we get it all back. Okay? And I think today I'll show you how we get it all back. But then for a deeper understanding, you'll have to be in 609 and learn tomorrow. Okay, that's where we're going. Good.
What happened to the 1 minus lambda?
Yeah, what happened to the 1 minus lambda? It's there. I guess maybe conceptually it gets absorbed into alpha. Yeah, it'd be a multiplier on all the z's, and so you can absorb it into alpha. Maybe that's the way to think about it. Any other questions? Yeah.
The analogy you gave earlier about using vectors, it was in the form of the states and actions you have taken in the past. But here the memory you have, it's in the form of gradients. So how are these two related?
Oh, in the table lookup case, the gradient is sort of 1 for the states you were in. Yeah, so that picture, and more generally, if you don't go to full function approximation, but have features that are plus 1 or 0, then it does map also onto visits to the feature, or occurrences of the feature. At those time steps, the gradient is unitary for the corresponding parameter. So the picture is like strictly true for the state tabular case, and I guess it's also going to be true for the feature visits. But in general, this algorithm is a totally general algorithm. If you did some other weird equation, like you did a deep neural network, you'd have to figure out what that gradient is. And could be positive, could be negative. Doesn't have to only have positive parts. It all works out. Yeah, the question was to connect the gradients to the picture of the fading traces. The fading always works out, right? Okay, good. Here is sort of the answer to the question, and showing that we've lost some things. So here's the offline lambda return performance. This is the same thing I showed you earlier. I just put it on the right-hand side. You maybe remember those curves. 0.8 does the best, and so forth. Now here we have TD lambda, and it's similar, very similar. Maybe there's a difference. Now I should say, these are random walk experiments. So I can do like lots and lots of runs. And I'm not showing you error bars because the error bars are so small. The error bars are like smaller than the line. Okay? Good empirical work. When you do your research, you'll want to show error bars. But probably for these random walk things, you don't need to. You just run it long enough that you know the answer very precisely. Okay? So I look at this and that number, and maybe this is just a little bit higher error. But I think what I'm more concerned about is the fact that, like 0.8, then remember this has this nice gradual degradation. Well, for TD lambda, it's not so nice. It loses as you go up to higher alpha. So we are lost something. If we get the right step size, maybe we've not lost much of anything. But it's not as robust to the parameter setting. Okay, and that's concern, because remember, this is just a small problem. This is the random walk, and in a larger problem, you'd expect that can you find one alpha that works for all parts of the problem? The robustness is quite important, and so it's still an open question. Can we get all the nice things we like about TD lambda? It's elegant algorithm, but still get this performance. And so there is a way to do it. And it's roughly true online. And I'm just going to tease you about it, hint at it, I guess. The first step is to realize we can do everything in an n-step form. See, n-step and lambda are not incompatible. you can do like a lambda return up to some horizon. So that's what we have here. This is a lambda thing, but it's instead of being up until the end of the episode, it's up to some horizon h. So this is from t to h. Let's do the lambda thing, the lambda return. And so instead, basically, this is the same equation where I've replaced the capital T, the end of the episode time, with a horizon which could be shorter than that. And like you could say, I want to do like a lambda weighting, but only up till 6 steps. And the reason you might want to do that is because then you only have to wait 6 steps. You don't have to wait to the end of the episode. You wait 6 steps and get something pretty close to the lambda return, because things tail off and they're less important. So that would be an idea for a n-step lambda return method. And you can do that, and that works pretty good. It's a little crufty. You get these funny time index things, and you get the delay by n steps, but you're not all the way to the end of the episode. And if you choose a reasonable n, this can do better than TD lambda. Cut the cost of the delay. But that's a nice thing. The real better thing to do is true online TD lambda. Okay? So this is, I'm stealing now from Joseph's talk, stealing his thunder. This is the performance of true online TD lambda. So if you see it, this is what we can get if we do TD lambda right. And it's really nice. The number is a little bit lower, maybe lower than this. And we degrade a little bit more gracefully. Remember, the lambda equals 0 line is the same in both graphs because it's just t to 0. And so this thing coming slightly below the line, whereas this one comes above the line, means we're really doing slightly better in degradation. And then look at this one, 0.75. This is better, more robust. So TD lambda, which I haven't explained to you, true online TD lambda is the it's it of TD lambdas. Okay, so this is what it is. Okay, I'm not going to really explain it in depth, but I can show you the algorithm. The algorithm is pretty simple. These equations are pretty close to the equations I gave you before. What's the difference? The difference are we've added this. If that wasn't present, we'd just have TD lambda, alpha delta z. That would be the whole thing. And we've just added this extra thing. And what do I want you to notice about this extra thing? It's all things you know, right? It's z and feature vectors and weight vectors. So it's everything you're familiar with. There are no matrix operations here. If you this is an inner product, that's an inner product. In fact, these are things that you already have lying around, because when you constructed delta, you had to compute these inner products, or some things very much like them. So this just says this is a small thing that you have, and when you subtract them, it's going to be a number. It's going to be a scalar. And then you're going to multiply it. This is a difference between vectors, and you're going to multiply it times the scalar. So it's all methods of complexity that's equal to the size of the vectors. If there's no square of the size of the vectors. Okay? And so there's that correction term, and then there's this bit. If this bit wasn't present, you just have the feature vector times 1 added in, which would be the gradient for the linear case. I should say the bad news. The bad news, I forgot to mention, the bad news is that true online TD lambda is a linear idea. It doesn't work for arbitrary nonlinear networks. But for the linear case, we can get really ideal performance. It's really as if it ends up with weights as if you waited till the end, but you don't have to wait to the end. You can do them right away, and of course you can't do the same weights as if you waited to the end, because you haven't waited to the end. You don't know what those signals are, but you can strangely enough, you can arrange it so that by the time you get to the end, it will be as if you knew what the end was, as if you were waiting and went to the end. Okay, now this strange eligibility trace, it's called a Dutch trace, and notice that it's also going to be cheap. These are alpha, gamma, lambda, these are all scalars, And this is an inner product of the feature vector with the eligibility trace. So that's going to be an inner product. It's going to be a number. So it's going to be 1 minus a number. It's going to be a scalar, and it's just going to be a small thing, except we do have to do this inner product. Okay, so where have we gotten to? Okay, if we want to think about the traces like this, we talked about the accumulating traces, where if something happens twice, it adds up. Or happens many times, it adds up. And there's another thing called replace traces, which is just like traces, except when you happen twice, you don't add up. You only just go back up to 1. You go up to a given height. And so even if you happen many, many times, you never go above 1. And Dutch traces, it turns out, are sort of an intermediate case. If it happens many times, you can go up some, but you're not going to go as high up as you would with an accumulating trace. And it depends actually on exactly the feature vectors that have occurred. So that's a little bit of a hint about how it works. 3 different kinds of traces. Maybe we've learned now in 2017, 3 years ago, we learned that we want to always use the Dutch traces. We can throw away these other 2. Well, this one's still kind of useful maybe if we want to do nonlinear networks. Okay, so to round out today, we have to talk about control. We'd like to do all these ideas in the case of control. And on the surface, it's easy. We just, we're going to do the same thing. Alpha, delta, z. Alpha is going to be, or delta is going to be now the action value form. So we're going to compare our guess given the state action pair, the guess to the new thing, also based on the state action pairs. And similarly, our traces are going to now, instead of be gradients of v hat, they're going to be gradients of q hat. But otherwise, the same idea. Of course, in the linear case, our feature vectors will depend on state action pairs. Okay, and then you can run and then you have an algorithm. It's appropriate to call it Sarsa lambda. I don't know what happened to my title. Bummer. I think it said something like control with traces. Sarsa lambda. This is mountain car performance. And it's just, what do you see? Well, I guess the title will just tell you what you would see. So we can just see what we see. On the right-hand side, we have the n-step methods. This is data from chapter 10. I've just reproduced it here. So it's mountain car with tile coding. Mountain car with tile coding, the same kind of tile coding. And we're just, instead of using the n-step method, we use Sarsa lambda. Sarsa lambda is just TD lambda, but done on state action pairs. Okay, and as before, for each individual value of lambda, we have a U-shaped curve. So we don't want our step size to be either too large or too small. We see that same kind of pattern, although we see a little bit of irregularity here. Like it looks like maybe I should be showing you error bars on these numbers because they're not reliably known. I just wanted to highlight that. These are also a little bit, I probably should have error bars here. Okay, but the pattern is clear. We have U-shaped curves, and we want to have a fairly high value of lambda. Do we go to any higher than 0.96? 0.98 and 0.99, yeah. If we go too high, too close to Monte Carlo, things go bad again, and we can even go unstable. And if we go too slow, lambda equals 0, one-step method. So that should be the same as the one-step method. So shouldn't these two be the same? The red curve and the lambda equals 0 curve. Maybe they are exactly the same. I think the right to left scales may be a little different. But it looks very similar. Those should be the same. And but then as we take lambda bigger, we can do much better. So there's all this area that we're filling in. We're getting much better performance by doing lambda rather than n-step methods. Okay? Okay, good. Yeah, so we're done for today. The major conclusions, the eligibility traces provide an efficient, elegant, incremental way to do Monte Carlo and TD. We can do, particularly give you a way to do Monte Carlo. Because we can change lambda equals 0, we can choose lambda equals 1, and we get effectively Monte Carlo, but we don't have to wait till the end. We can update as we go along. It's an incremental way to do Monte Carlo. I mean, we sort of had that available with, we could have done n-step methods with a large n, but then we are basically waiting till the end. We're waiting a really long time before doing the updates, so there's a big delay. It's really a much better way to do Monte Carlo. And true online TD lambda is the best, probably of the current choices, because it's going to be exactly equivalent to doing a lambda return algorithm. We've seen the 3 kinds of traces. Dutch is the kind of traces that are used in TD lambda, but it's interesting. You can use Dutch traces without doing the full TD lambda algorithm. And it's not clear that you need to do the full TD lambda algorithm. Maybe you can do just Dutch traces, which is that particular form of traces that are used in the algorithm. And so we can do it for prediction and control. Everything we've seen today is on policy, holding off on the off policy stuff. There's a general pattern that the eligibility traces methods seem to perform slightly better than n-step methods at the cost of this computation, maybe twice. Okay, so questions? Traces, introduction to eligibility traces. Yeah. Adam, thank you.
Why are they called Dutch traces? That's a weird name.
Why are they called Dutch traces? Well, there's 2 reasons. The most important one is we can't think of a better name for them. Okay? Yeah, Dutch, we tried so many things to try some name that evokes the actual substance of them. Which, I always complain about names that are named after people and stuff like that. So in this case, it's named after some people. But they're not just particular people. There are some scientists that were working here, and they were Dutch. So they both happen to be Dutch that invented this algorithm. And so I started calling it Dutch traces, and it's just a label. And it's fun, a little fun to say. It's important that a name be fun to say, like Q learning, Q value. This should be fun to say. And Dutch traces is kind of fun to say. There's kind of a little alliteration, traces and Dutch. I don't know. It seems to work for me. And I can't think of a more descriptive name. I mean, people have thought of horrible names based on, what do they call them? Anticipatory traces or all kinds of weird names. Yeah, if you can think of a better one, I will change the book. Absolutely. But so far we can't think of a better name. Otto van Hasselt and Harm van Zijen are the 2 Dutch guys that are most responsible for this algorithm. The effect is somewhat similar in that credit will be passed many steps. Prioritized replay is probably better because remember the problem with traces? Remember the problem with n-step methods for long n is that you find some roundabout way to get to the goal, and all of those steps get locked in, get stamped in, which is good. But it's only kind of good because it's good because you learned the whole thing, but then the next time you'll tend to follow that. And what if it was a roundabout way you got to it? You kind of learn, stamp in that roundabout way. But methods like prioritized sweeping, which would be based on a model of the world, they are not subject to that problem. They all the ways go in are less subject to that problem. Model-based methods are more powerful. And so the things like the traces and the n-step methods are attempts to get some of that benefit without going to the immense complexity of a model-based method. Because model-based methods are huge. They're like a value function is size of the state space, or size of the state action space. A trace is size of the state action space. Okay, but a model of the world takes a state action and it'll tell you the next state you're going to be in. So it's really like states cross states. It's a much larger object, the model. And so we want to do what we can do in the small space before we go to models and then eventually combine them. And so traces are still staying within the scope of just a value function rather than a whole model. Good question. Any other questions? Adam.
I feel like when I've read about modern deep learning systems like EQN and other things like that, they don't seem to use eligibility traces. Is there a reason for that?
So modern methods, modern deep QN methods, they do tend to use n-step methods. They've realized that you don't want to do only one-step methods. That multi-step bootstrapping is a real win by the measures that they're concerned with. Now, of course, there's all sorts of different communities. Many of them don't use eligibility traces, but many of them do. Yeah. Why would you not? I mean, one reason you might not want to do it, if you have a simulator, if you're really training from a simulator, then you'd just be happy to generate more real experience rather than try to get a little bit more out of your limited experience. Yeah, I'm not sure I'm ready to make a statement about whether they use it or they don't use it. But yeah, it's true. What's true? What's true is that they would consider it an advanced topic. Okay, and we put it here in chapter 12, near the end of the book. But really, for me, the very first algorithm was TD lambda. The TD lambda paper is 1988. So we were doing TD lambda before we knew all the other things. It was just such a simple algorithm. We could imagine the brain doing it. We could imagine a machine doing it. Now, a lot of things depend upon the architectures of digital computers. So a trace, you compute this thing, say at the connection weight, and it fades away. And so it's a really local in terms of information flow. You don't have to communicate with any other weights. Okay, that weight has something, and that weight thing is fading. So the flow of information is very good, but on a von Neumann computer, it doesn't matter. Von Neumann computer, you just access memory, you move it into a register, and you operate on it. So you don't. The locality is not an advantage to them. And so a lot of these guys using, they just say, oh, I don't want to do traces because I have to do two vector updates. And it's not computationally efficient. But I think that depends on how what's your model of your machine and so forth. So on a different machine, it might be really even less expensive. Okay, any other comments? Did you have a comment? No, okay. Good. Well, thank you all. We'll see you next week.